Thank you, Ben, for inviting me and for organizing such a nice workshop. What I wanted to talk to you today about is entitled Selling Experiments, and it's joint work with Alessandro Bonatti from MIT Sloan and Alex Molin, who's a graduate student at Yale. The title Selling Experiment really refers to the notion of experiment as suggested or analyzed by Blackwell. So we want to talk about information structures or information, and in particular I want to talk about how to sell and buy information. I want to talk about how to package information, and I want to talk about how to price information. Okay, so the basic framework that we are interested in studying here is really what we suggest is sort of a fairly canonical framework. We want to think about the decision maker under uncertainty who has coming into decision some partial information about the problem that he needs to solve. That information to him is private. And what he can deliberate about is whether he wants to acquire some additional information to augment his initial partial information. And for that reason, we're going to call the decision maker, often refer to him as a data buyer. And on the other hand, there is a data seller who has the ability to augment the buyer's information by additional information that will help the data buyer in terms of making a better decision, a more informed decision. And for him, the question is, how much information should I provide? And how do I provide it? And how do I price the information that I'm going to provide? Okay? And given that the buyers have different, possibly private information about the decision problem at hand, it might very well be that I may want to offer different pieces of information to different buyers, and so then I will have to think about how to match the initial information of the buyer with some additional augmented information that is coming from the seller, and maybe I want to offer different matches in terms of initial and complementary information across buyers. And the leading interpretation is we want to sell access to a database. Okay, so we have a large database, a pre-installed database, and the data buyer can basically be granted access, partial, limited, restricted access to the database, and we want to know how should we price access to the database. We sort of stumbled a little bit on this problem in earlier work with Alessandro, when we were interested in targeting and advertising on the internet. And so in our mind, at least, the leading example is the one of selling information about customers. Okay, so maybe just as an interpretation or as an example to keep in mind, firms that sell their own product have a choice to tailor advertising to the different users. Of course, they can choose to target particular users, but that requires information about the characteristics of the user. Say I only want to target young males between 25 and 45, say. Let's make that 55, including young males, okay? And so what we want to think about is data sellers, data brokers, intermediaries having collected information on individual users' attributes and characteristics that they can offer for sale. And the attributes that are already stored in the database differ in terms of what they explain, to which characteristics they speak, how good that information is. Okay? And crucially, in the setting, the firms may already have some partial information about the consumer. So since they have already interacted with their consumer base, they may have some information already about users in terms of their geography, in terms of their income, in terms of their past purchase history. So the issue is really how to combine initial information with additionally incremental information. Okay. So the setting is that we're going to think about the data seller as offering an information product. That's really going to be an experiment in the sense of Blackwell. An experiment is going to reveal information about the decisions maker's pair of relevant state. And of course, what the value of the experiment is that is being offered to the decision maker will depend on the amount of private information, on the amount of initial information that the that the buyer already has. Okay? By contrast, the data seller simply has a prior distribution over the nature of the types or beliefs that the buyers have. Okay, so he faces a problem of trying to possibly wanting to distinguish different types, different buyers in his market. Okay, and so what the analysis is hopefully trying to convey is that there are ways in which I want to version information, that I want to package information, and we're going to squarely today focus on the situation where only the information product itself is contractable, so situations where I can only contract and price the experiment itself. I can't contract on exposed data, that is, I cannot contract on decisions, say, that the decision maker later on made, so sort of revenue sharing, or that is not going to be considered, nor can we contract on the exposed realization of the pair of relevant state. Okay? And for most of it, though, clearly we can think about extensions. We're going to think about the data seller having the database already installed so that there's a zero marginal cost for him of providing more or less information. Okay. Okay. Of course, we're not the first one to think about information, pricing information, selling information. Let me perhaps just make the observation that in the context where we actually have an explicit pricing of information, so where we're valuing information, mostly what has been considered in literature is selling the entire random variable, is selling the entire distribution of pair of relevant states against a completely uninformed buyer. That's sort of the classic work of Admati and Fleiderer. And then on the other hand, when one sells information, people have looked at what is the price of buying particular realizations of the random variable, so access to particular realizations. The question of how to version information, sort of in a fairly, canonical, as in Blackwell sense, hasn't been posed to the best of our knowledge. Okay? So what are the main results? We're going to show that it's optimal for the seller to offer a menu of experiments. The menu is going to contain only relatively simple experiments, and of course I'm going to describe what I mean by simple. The menu also is going to have the feature that it's much coarser than the set of types. So if you think about what is the mapping from type to allocation, it will be the case that we only will offer very few experiments relative to the diversity and the heterogeneity in terms of information. To the extent that we're going to offer several information products, naturally they're going to differ. Naturally, therefore, they're going to be distortion. That is, not everybody is going to get perfect information. And the way we're going to distort is basically by directing information and basically trying in the incentive constraint to sustain or the incentive constraints, we'll come to that, but are basically going to try to capture the idea that on equilibrium or in truth telling, I'm only going to make type 2 errors statistically, so I only will have false positives. And if I were to misreport, I'm going to try to induce type 1 errors, that is false negatives. Okay? Part of the coarseness and the limited information that's going to be provided is going to come through the fact that once we investigate what the payoff functions are looking like, we'll find out that the payoff functions are linear in the probabilities. And so that will remind us of sort of classic monopoly problems in which we are not selling in the absence of convex cost, in which we're not selling intermediate versions, but we're rather selling the object in its entirety or the object not at all. Here, the reason that we're going to have intermediate solution is going to have to do with a specific problem and the specific way in which types and incentive constraints arise in a Bayesian world, where we basically will see sort of a garbling in some sense, or a distribution of types, not starting from one of the ends, but starting from the middle. So the geometry, in some sense, of the problem that we're looking here is quite different from the monopoly problem, at least globally. Okay, good. So the decision maker, the buyer of information, the data buyer, he has faces uncertainty. Uncertainty is encoded by a finite set of states. In order to respond to the uncertainty, he has access to a finite set of actions. And for most of the talk, I'm going to look at a binary world, because then I can sort of illustrate and use some geometry, but the qualitative results, as I will state them at the end, are going to generalize to an arbitrary finite setting. Okay? But crucially, even in the binary world, where there are just two actions and just two states, the specification of the buyer's private information is, of course, much richer, because they basically include all possible posteriors that the buyer may have about the probability of one state against the other one. So that is already a continuum. Buyer and seller start out by sharing a common prior probability over the states, let that denote by mu. But before they starting interacting, the decision maker may privately observe an informative signal, or likewise, the signal is going to induce an interim belief or an initial belief of the buyer over the underlying states of the world. Okay? And so this is where we're going to start with. We're going to say these initial beliefs that, of course, by base consistency going to correspond to the common prior, form the private information that the decision maker has. Okay? How much he knows about every state, that's encoded in this probability vector theta. That is his private information. And all the initial data that the seller has, the data seller, is that he shares a distribution of initial beliefs over or prior over these beliefs that the buyers have. What he then can offer in terms of augmenting and complementing the information that the decision maker has already is essentially an experiment, an information structure. So that's simply going to be a set of signals S and a likelihood function pi that gains meaning, or the signals gain meanings to this likelihood function that simply relate the underlying state of the world omega to the realization of the signals S. Okay? And the seller basically can offer a priori an unrestricted menu of experiments, where each one of these items on the menu is going to form an entire experiment, and he can charge a price for that particular experiment. Okay, so our sort of interpretation is here. I'm basically going to price access to database query. I'm happy to buy the access before the state omega is realized. The data is already stored, and so what is priced is the quality of the data that is being provided. Okay? The initial signal and the incremental signals are independent conditionally on the state of the world or the pair of relevant state omega. Okay? Right, so to then make it precise, so the interim probability or the initial information that the buyer has when he enters or starts deliberating of how much information to acquire is simply a vector theta or a probability for every single one of the states omega that tells him what is my posterior probability that this state is omega I. Okay? The experiment is sort of best characterized by a likelihood function that tells me what's the conditional probability that a signal Sj is realized given that the true underlying state is omega I. Okay, we're going to use a little language that's sort of evident. We're going to call perfect information any information structure that has a 1 in exactly one entry in one row of the information matrix and 0 everywhere else. We're going to call extremal information any information structure that has at least one row with just a 1 and zeros, but the other ones can be non-negative numbers. Okay. The bias payoff exposed. The utility of the decision maker is simply the utility that you would get if you choose action A and the true state were omega, without loss of generality, in the sense that everything else would just involve a scaling or a reweighting of the probabilities. We're going to look at a situation where what the decision maker is going to try to do is to match the action with the state.
So is this without loss of generality because we're in binary states, binary actions?
No, this is without loss of generality for the finite, more generally. Without loss of generality for the theorems that I'm going to give you. Right? So all that would happen if I were to, here when I'm thinking about what's the difference between choosing action AI and action AJ, it's 1 minus 0, right? If there were general utility function, then I would just have differences everywhere. And in terms of forming expected values, all that would happen is that I would reweigh the probabilities by the utility differences.
But should this be obvious that this is the same as the case where, for example, I have 3 actions, actions that I take in case of uncertainty? And
I'm saying for the results, for the characterization of what optimal information structures look like, the same results would hold for a more general setting. But for the moment, we're going to look at a finite action, finite state. So we have symmetry between actions and state. And I want to match the true underlying state with the action. If I succeed, I'm getting a 1. If I fail, I'm getting a 0. Okay? Good. So this is, of course, just a description of the exposed utility of the decision maker that he will typically not have the privilege to be accessible or available to him. If he were to make a decision just on the basis of his initial information, then he would simply choose that action which maximizes the expected value, okay? Given the belief that theta allows him to have. We can then think about the value of the experiment as a net value of the augmented information, right? So what we're going to do is we're basically now going to have access to an experiment. That experiment is going to induce beliefs about what's the likelihood of different signals. And given my belief and given my signal, I then can make for every signal a decision that is optimal given the information that I have. And I'm going to form the expectations given a particular experiment that I avail myself as a decision maker. The value of the experiment then from the point of view of the decision maker is simply the difference between the realized or the expected utility given the experiment minus what he would have achieved in the absence of access to the experiment. Okay? So if you think in particular about u of theta as being the outside option of the agent, right? Then what we see here is that clearly the outside option is type dependent because the better information have the higher value do I have in absence of getting access or being granted access to the experiment. And similar from the point of view of the data seller, what I'm going to try to extract is the value of the experiment, I mean the net contribution that the experiment is going to provide over and above the already existing information of the data buyer.
I might be missing something, but so by looking at the seller presumably can look at the outcome of the experiment. No?
No. So I mean he can look, okay, but what we're going to assume is that I can't contract on the outcome of the experiment. That is, I cannot. So in the I haven't set up the mechanism design problem or the selling problem yet, but what I prefaced is that the prices, the transfers, cannot be made contingent on the exposed realizations of the state, nor on the actions that the agent is going to take.
Right, but so if I look at the experiment, the seller could learn something about the distribution of theta, then intuitively shouldn't that also help the seller learn something about the distribution of the buyer's beliefs about theta? I guess what I'm asking for is how would you microfound this assumption that whatever the outcome of the experiment, the seller has the same belief with the distribution of the buyer's beliefs?
Oh, so simply think about going back to our internet advertising. So what we're interested in are the characteristics of the buyers. Okay, say Macy's is going to make a decision: do I want to run an advertising campaign against a certain number of shoppers that show up on my website? Okay, do I want to offer them a special deal? Macy's clearly has some information about these buyers, but they can acquire more information from a database, okay, that will have a whole kind of other characteristics and attributes available that has simply been collected through other interactions of that buyer with other sellers, right? So now I can clearly ask that I'm being granted access to these additional attributes and characteristics. That is, what is my purchase profile? What are my additional demographic characteristics? Okay, and that's what I'm trying to get at. Good. So and hopefully will become clear when we go sort of through examples, or clearer. This is the general formulation of the value of experiment now for arbitrary utility functions. If indeed we're going to have symmetry and matching with the state, then the value of the experiment for a buyer who comes in with a initial belief theta can be simply written in the simple form. Okay? Simply because in the absence of any information, so that is this abstraction, I'm going to choose that alternative that has the highest prior, as it were. Okay? And in the presence of a signal, for every signal j or sj that's being realized, I'm going to choose that alternative that has the highest posterior probability, which is simply the product between theta I and pi ij. Okay? And I'm going to do that for every signal. And the difference, in some sense, the number of times that my decision changes relative to the decision in the absence of information is what my value of information is. Not quite sure whether that's helpful, but here is sort of a visualization, right? So think about 3 states. We're going to reduce it for the obvious reasons later on to 2 states, but just to give you sort of an idea. The interim beliefs are theta 1 and theta 2. The third one, of course, is the adding up constraint, so we don't have to plot it. And then I'm going to simply say, what is the value that arises from the perfect information experiment? What is the value of the experiment for a buyer who has a prior theta 1 and theta 2? Okay? So on the x-axis, you have theta 1. On the y-axis, you have theta 2. Since they have to add up, I took a perspective that covers a little bit of the plane on which theta 1 and theta 2 are lying, but basically the northeast it has to be empty because that's a violation of the probability simplex. And then what we see is that the peak of this little pyramid is precisely when the buyer is uninformed. That is when theta 1 is equal to theta 2 is equal to 1/3. And then it falls down on each facet and hits 0. Okay? This is maybe slightly better perspective to take on. Again, we're thinking about the value of the experiment for a given experiment. So here I took, just to give you an idea of what the nature of the payoff functions are and what sort of the structure of the payoff function is. I gave you an asymmetric information structure. One in which signal 3 actually informs me perfectly about the underlying state omega 1, but in which S1 and S2 are noisy signals. Okay? And again, I can ask myself, what is the value that experiment has for agents with prior theta 1 and theta 2.
Just to clarify, for this interpretation, it's important that the buyer's private information is independent, conditional of the state from what's in the database?
Yes.
It cannot be that the information that the buyer has is basically having seen some part of the database before, because we need this conditional independence.
Yes, or if a priori they were conditionally dependent, then what I would like to do is to rewrite it so that from the point of view of the buyer, I'm going to look at what is the value of the independent increment. Okay, so I could do that, but it's simpler to start right away with the independence. I would get another dimension of complication that I don't think I know how to handle if different buyers had different correlations with the underlying database. That's an interesting question. Okay. Well, so it's okay. So it's an interesting question. It may maybe we can address it in the following sense: that if there were in fact this correlation, then in some sense it's a limit. It is a restriction on the value of the service that the database can provide, because it basically has some correlation. So the incremental value is not that high, and it's a limit more on the data seller rather than on the data buyer. But of course, there's also a question then of information extraction. So yes. So okay, but nonetheless, what you should glance from this visualization immediately is that basically the value to information is highly irregular in the sense that there are going to be many kinks, but there are going to be lots of phases. That is, there are going to be lots of places where the utility is linear. Okay? And the interesting thing happened at the vertices or the edges. And basically what happens to them is that as we go through an edge or go through vertex, the decision that the decision maker with now a slightly different prior is going to take vis-a-vis the same information received is going to change, and that is going to induce the kink in the value function. Okay? So, but basically what we're going to see is piecewise linear utilities, but plenty of edges and vertices that the optimal information structure or any information structure is naturally generating. I said maybe just extreme before. It is that there are some rows, right? So I'm going to write the information structure always that I'll enter in a row the state and in the column the signal. Okay, so it will have to be that every row adds up to 1, hopefully does. And an extremal experiment is one in which at least one of the rows has the feature that there's only one positive entry and all the others are zeros. Okay, so that if you think about the set of all possible experiments, then these are the extremal experiments in the sense that we reach the boundary. Okay? That we can't reconstitute that information structure through another convex combination structure through other. Okay. Here's the problem then formally that the seller is going to try to solve. So the seller's problem is he can offer a menu consisting of experiments and transfers. It is otherwise a standard static mechanism design problem, so we can appeal to the revelation principle, and we basically can write down the problem from the seller's point of view, that is to choose a set of experiments and associate transfers such that the net utility of the transfers is maximized. And what I want to make sure is that I match the bias with the information. So the first set of incentive constraints are going to be met for all possible pairs of types, theta and theta prime. And then second, that I'm going to satisfy the participation constraint, that is the net utility that is the bias being left with of every type is non-negative. So now I'm going to try to give you basically a set of results that will eventually lead us to a fairly comprehensive characterization of what the optimal information structure is. Okay. Clearly, even though we have just a finite number of states for the moment and a finite number of actions, the set of information structure is much larger because we basically can choose probability distributions in terms of these matrices. So the space of information structure is much larger than this underlying decision problem. Okay. And there is also then the sense that we will have, in some sense, a too large a space in terms of the information structure, because after all, what we're trying to do is simply to match the information to the actions. And so that suggests that we will never need more signals in some sense as there are actions available, because at the end of the day, all that we want to do is that that signal leads us to an action, and two different signals that leads us to the same actions are in some sense not valuable for the decision maker, and in fact maybe costly from the point of view of the seller because they offer more incentive constraints. Okay?
I would have thought the more general version of this lemma would be that what you want, and this is where I don't understand why it's matching actions and states without loss of generality in the general model. Take a general model with finitely many actions and finitely many states. I would have thought this lemma would say you don't need more than the minimum of the cardinality of the action space and the cardinality of the state space. That you could always get to the optimum by having number of singular realizations at the minimum of the cardinality of those two sets, being silent as to whether the set of actions or the set of states is bigger than one another. I don't know how to think about that given this whole matching actions and states.
No. So, but I guess
because there
the generalization would be in effect exactly be this one. At most, we need the number of actions that we have to choose.
But I think if there's fewer states than actions, then you don't need more than the states.
Well, okay.
So I think it's
Sorry, no, that's true. That is the set of actions that are chosen optimally. Yes, yes. So then your qualification is correct. Right. If we have fewer states than action, then instead some actions are already redundant, and so therefore the stronger constraint binds. Yes.
So but he's saying it's not actions chosen for some belief. It's
just
actions chosen given knowledge of the state.
No, but you know, I guess it's sufficient to look take the ex post perspective. Right, and so therefore, if there are at most k states, possibly more than k actions, nonetheless, I know that.
But in general, it's not without loss of generality to say you're not going to take more actions optimally than states, right?
Sometimes
you want to take a medium. Sometimes it could be I have actions that I want to take when I'm sure of the states, and there's like an insurance action I take in the center. So I don't know when this was ruled out.
Yes.
But it was ruled out?
No, so I'm going to state this for precisely the symmetry matching, yes. No, so you're right. We didn't rule this out, and so let me today, even though I made maybe the slightly bold claim in the beginning, when I state the lemmas in particular, we can talk then again about the theorems. For the moment, just about the symmetric environment of matching state. Absolutely, yeah.
The experiments are being distinguished when you're selling the same experiment. You defined I as an experiment.
Yes.
But you might sell it to two different thetas. But I think for the lemma, you're distinguishing those two.
Right. So it's important. So a menu is basically all the options that are offered for sale, and the items on the menu are the experiments. Okay. So every buyer, that is every type, theta, buys at most one experiment. And every one of those experiments which is in the menu consists of at most cardinality of A signals. Right? So every type chooses in this menu, there are many experiments, but I'm just going to choose one experiment. But that experiment is then characterized by its likelihood function and the signals. And it's sufficient to look at experiments whose cardinality does not exceed the number of actions available to the agents. Okay? And so the argument is quite simple here. If we think about the value of additional signals that are in the experiment and that are meant for the type theta, okay, then if two signals will lead type theta to choose the same action, then clearly distinguishing these two signals have no value for him. Okay? On the other hand, distinguishing these two signals may have value for another type who could now be tempted to buy this experiment, and therefore I'm going to be able, as the data seller, to tighten the incentive constraints by actually merging these two signals. Okay? Because now I'm going to lower the value for other possible types. And so that is what drives me to offer a menu where in the menu every experiment has a minimal set of signals. Okay. Okay. And then now, indeed, to sort of be able to characterize the exact information structure and use some of the optimal mechanism design environment, I'm going to specify even further, narrow our intention even further to a model, to a binary model where we just have a binary action, a low and a high, and the state, a low and a high. Okay? And given the coarseness of the signals, that is that they match the actions, I know now that in this binary world, I can immediately restrict my attention to an information structure that reflects that binary environment, namely a low and a high signal that has entries alpha and beta on the diagonal. Okay? And we're simply going to work with the convention that alpha and beta is larger than 1, meaning that we're going to identify as H and as L as the signals that more naturally convey the low state and the high state respectively. Okay, so every row adds up to 1 clearly, but there's no additional requirement in the columns. Okay. Right. And so with that restriction to a binary world, we can now also restrict theta, the vector of probabilities, to just describe the probability that the state is high. Okay? And then we can rewrite the max minus max value of experiment expression here in terms of just these two parameters alpha and beta. Okay? Yeah, so that now we see there is a one-dimensional uncertainty in terms of what the true theta is, and there is a two-dimensional instrument, namely a choice of alpha and beta in terms of the information structure. Okay, right, so the first term is simply the adding up of the weighted probabilities, alpha and beta, and the right term is simply choosing whatever is the alternative that has the highest probability from an ex-ante point of view. Okay? It's clear what a perfectly informative experiment is. We're going to call a directionally informative experiment 1, in which there's only 1, not 2 rows which have 0 and 1s. Okay? And it's directionally informative in the sense that the information is valuable for some types, that is for some prior beliefs, but it's not valuable for some others. Okay? So if I'm going to receive the low signal here, then clearly, no matter what my prior is, I'm always going to learn that the state is a low, and I'm going to choose a low action. Whereas this noisy signal as H, that is still possible to be generated under both of these states, is only valuable in the sense that it redirects me from choosing a low action, a high action, for somebody who believes initially that the high state is very likely. Okay? And so this is directional information in the sense that this is only valuable if I'm already tending in the direction of a high state, but it has no value if my prior is such that I'm assigning a high probability to the low state anyway. Right? So now let me just plot you a little bit more, and then to give you a sense of what the incentive problems are that are arising. Right? So if I'm going to look at the perfectly informative experiment, where I'm going to tell everybody precisely what the state is, then I can plot what the value of the experiment is as a function of the underlying type theta. Okay? And what you observe now here is that clearly the value of that experiment is highest for the type who initially is undecided between whether the state is low and high, so theta is equal to 1/2. So from the point of view of, who is the efficient type or who is the type who values the experiment highly, it's now not an exterior type, it's an interior type. And then going down in each direction, I'm going to assign less value because my prior information was already sufficiently good. At the bottom, of course, at 0 and 1, I already know with certainty what the true state is, so therefore the value of the experiment, even though it's perfect, is going to be 0. Right? Think about a slightly different experiment, a directionally informative experiment, where it's giving me perfect information in one row, but less than perfect information in the other row. Okay? Now, that was precisely the example that we looked before. Okay? Now you see that the payoff function that emerges is slanted towards the right. Okay? Namely, somebody who has a prior coming in that the state is low with a very high probability, he's not going to change his mind after observing the noisy signal. He's still going to choose the low action. And therefore, the value of the signal is 0 to him for the longest time until at the kink, where we now have a rise in the utility function on the value function, he would change his mind. Okay? So one thing that immediately illustrates to us is the fact that just the distance from the center from point half is not sufficient anymore to describe the value of an arbitrary experiment. Okay? Because I have my value declines slow in one direction and declines faster in the other direction. Okay? Right, so now what we see is basically that even though in terms of the prior probability we have a one-dimensional incentive problem, in terms of the incentives, the highest type is not in the exterior, and in terms of the incentive constraint, locally they look quite different. Okay? If I move down to the left or down to the right, they are not the same. Right? So I can rewrite this now. I can just, so that I can put names to the labels, I can say, let me call beta the probability that I put on a low signal being generated in low state as the baseline informativeness, and let me call alpha minus beta simply the relative informativeness in the high state relatively to the low state. Okay. Right, so what are the sets of experiments that I can offer? Okay. These are basically the set of experiments that are now plotted in this space in terms of baseline informativeness and relative informativeness. Okay, so again, conveying the idea that the design problem here is going to be two-dimensional because I can make a choice both in terms of the informativeness in the low state and then the additional incremental informativeness that I allow to the signal in the high state. Okay, what I'm going to try to convince you now is that nonetheless we can reduce it to a one-dimensional problem. Okay, so first of all, think about this. I guess it's a trapezoid. What are the indifference curves look like? Well, they're going to all move in the northeast, and depending on how high your type is, you're going to have a different pivoting of the indifference curves. Just east or just north, okay? Right. But what is sort of important to notice is if I'm going to keep the relative informativeness constant, that is alpha minus b constant, then it is the case that changing the baseline informatives now is increasing the utility of all bias by a constant amount delta, okay? So what this tells me is that even though I might be worried about incentive constraints, whatever I'm thinking of offering in terms of the relative informativeness, okay, as long as I keep it constant, if I'm just increasing the baseline informativeness, that has positive value, uniform positive value for all of the agents. So what this tells me is that in some sense, the set of experiments that I ever want to use are the experiments which are on the boundary of that set, which are on the northern face and on the northeastern face of that experiment. Okay? And so now we basically have, again, a one-dimensional problem because we convinced ourselves that I can extract more value from all of the types by simply increasing the baseline informativeness uniformly. Okay? And so the problem that we now face is to basically make a choice of Q, okay, or reparameterize the boundary so that we have a description of what our optimal choices are. Okay? So in other words, we know that in the optimal menu, every experiment that we're going to use has to have either alpha equal to 1 or beta equal to 1. That is just the characterization of that boundary. Okay? So one of the rows has to have the feature that's entry of just zeros followed by 1. Not necessarily both, but at least one. And that's precisely then also the statement that's going to hold true in the finite dimensional environment. So we now basically have this parameterization in terms of an experiment in Q, which is just the informativeness, or relative informativeness, which can vary from from -1 to +1. The experiments which are at the extremes are entirely uninformative. The experiment that sets Q equal to 0 is the most valuable. That's a perfect informativeness in this reparameterization. Okay? But if you do look now at the utility function that we have up here for the buyer, then what you do find is that that is now a problem that looks much more familiar in terms of the literature on nonlinear pricing, right? Because we have to make a choice in terms of quantity Q that evidently satisfies the single crossing property with respect to the private information theta. It's a little bit more elaborate than the classic nonlinear pricing because you have the max and min operator, but at least you get the sense that we are now sort of getting ready to employ sort of standard machinery. The important part is so that it's the interior point that has the highest value, and it's also the case that types equally far away from 1/2 disagree on the ranking of imperfect experiments. So this is the aspect of directional information, that we don't necessarily value equally far experiments equally. Okay? Right. So optimal experiments, we therefore know, must be directionally informative. And so Q positive means that this is going to be information that is noisy when coming with the high signal, but if I were to enter with a sufficiently strong prior on the high state, it would tend to lead me to change my decision from relatively to the low signal now to the high signal with a positive action. On the other hand, if Q is negative, then it reverses the direction, and the value is now on the side on the left-hand side, where I think a priori that the low state is very high. Right? So let's just see what that then leads to in terms of the optimal information that is going to be offered when we have just two types. Okay, so the one type believes that it's likely that the state is low. The other one believes that it's likely that the state is high. And we intentionally chose them not to be symmetric, so that in a sense the type which assigns probability 7/10 to the high state is less informed. It's closer to 1/2. Okay. If I were to offer him, after all, he's sort of closer to the uninformed agent. If I were to offer him a fully informative experiment and were to try to extract it so that I basically leave him with a residual utility just at 0, okay, that's what I'm plotting here. Then I would basically just shift the triangle that we saw describes the experiment with perfect information downwards, okay. But in fact, I would shift it so much downwards that an agent who has a type 2/10, that is, he believes that the low state is likely, would now experience a negative value, and so he would not buy. Okay. The IC constraint, okay, doesn't rule out that I'm offering him some information. What it does now rule out is that I'm giving him perfect information. So what I can offer him now is I give him a directionally informative signal, which helps him at least sometimes making the right decision in terms of choosing the low state. Okay? And you see it has a different shape now. And I can indeed separate the two types, but because we find now that the agent 7/10 would not even want to bother buying this directionally or partially informative information structure because it would give him a utility that is negative. Okay, so in fact, this is not the optimal information structure because clearly what I would like to do now is to provide more information even in the partial experiment. So what we'll see is that as I change now, I'm going to increase the slope of the partially informative utility function, and that is simply expressing the fact that I'm going to give him more information, okay? And I'm giving him more and more information until I come to the point where the less informed buyer on the other side is just indifferent between buying either one or buying none, okay? And so what we now see is that we actually do provide two different information structure. We certainly provide the fully informative information structure, but we also give a just directionally informative information structure. And incentive constraints matter and bind, but in fact, or even the participation constraints matter. Okay, so it's not that we're creating the social surplus, but we're extracting all the surpluses created by the experiments. Okay, so there's, in that sense, surplus extraction and no information rent. So that's just the summary, and so the rest of the time I want to spend a little bit on what is the solution to the problem where we now have a continuum of type. After all, we are in a binary state, but the priors couldn't vary between 0 and 1. Okay? So before I sort of do that, let me just give you one more picture. Okay, and that is the following one. That is what we see in the terms of the global payoff functions. Okay, we see a picture that's quite different from the one that we normally see in Spence-Mielis environments, because the highest type is in the interior, and there are directionally or locally different values in incentive constraints that degrade at different speed. Okay, but if I just were to blow up, okay, the payoff function, so that on the right-hand side, I apologize that the labels are a little small, but on the right-hand side, I simply look at the payoff that as it varies with the type between 0 and 0.5. Okay. What we see there is actually that the utility function is just perfectly linear. Okay? So locally, or to the left of 0.5, this is in some sense just a standard monopoly problem, where I simply have a utility that is linearly increasing the quantity that I'm selling. And so what this would suggest that is locally, I'm just going to try to find the point where the trade-off between the inframarginal bias and the marginal bias is achieved. Okay, so I would sell to some types sufficiently close to 0.5. I would to sell to them the fully efficient, the perfect experiment, and the other ones I would not provide any information. Okay. We saw in the example with just two types that is not the optimal solution. That will also not remain the optimal solution in the case with the continuum of types. And so what is the optimal solution? That's what I want to now describe briefly. Okay. Right. And the idea, if you think about it, comes really from the fact that if you look at the interior point, in particular if you look at the type equal to 1/2, okay, if I just do the regular sort of Mielisian trick, that is I'm simply trying to get out to the indirect utility of the interior type, okay, then it's true that the local incentive constraints are completely characterizing the indirect utility that I need to give to the higher types as I'm moving towards 1/2. Okay? But then there's going to be a second constraint which says that actually, whether I'm approaching him from the left or I'm approaching him from the right, it must be the same value that I'm attaining. Okay, and so now, besides the local constraint, we're going to face global constraint, and it's the nature of the global constraint that then will force us to interior solutions, but to only a few interior solutions in terms of the experiment. Okay, right? So we have a single crossing in this utility function, okay, and I could describe what should be the rent of the agent who is the most efficient type. They would have to add up locally by the Spence-Mirrlees conditions, okay? But they would have to add up whether I'm approaching upwards from 0 or I'm approaching downwards from 1, okay? Okay, and if I'm just going to rewrite this value function with our state matching utility, then what this utility has to be, whether I'm coming from the left or from the right, is the expression in the integral, which is simply the quantity of information Q provided, okay? And that therefore, in this environment, the allocation Q is implementable if and only if that Q is non-decreasing. That's the regular monotonicity condition. And it so happens that with the uniform utilities, the symmetric utilities, the integral over the information provided has to add up to 0. That's just a representation of this integral constraint. Okay? And so we have now local as well as these global constraints. Okay? And so rewriting this now using virtual utility functions. Okay? Here's a problem that the seller has to face. Okay? It's piecewise linear and hence concave, but it has the integral constraints. The observation to make this is in the absence of the integral constraints, we would have indeed just -1 and 1, which is 0 information, or 0, which means full information. And in that case, we would simply have a flat price, namely 1 for the perfectly informative information sensors. We would have just very limited information being offered in the market. Okay? What we're going to find now is that that will typically not be the case. It will be the case, though, if we are in a world where the incentive constraint only matter from one direction. So if I think about the truncated support, where somehow the priors are all on one side of 1/2, then indeed we would just have just integer solution at 0 and 1. Okay. Okay. And so the result that I'm going to try to sketch a little bit is to say that in this binary world, we're going to see at most 2 experiments being part of the menu. Okay, so that's the second part in which we now have a course menu because we're just offering 2 experiments. One will always have to be the fully informative one. The other one is going to be one that is directionally informative. So in that sense of the word extreme in our definition. Okay. Okay. So maybe just a little bit. Right. So the issue now is that we have this integral constraint. And what that integral constraint does, beyond it not being a local condition, is that also the Q now is going to weigh elements of the virtual utility function different. So we're going to have the situation that what the virtual value is going to depend on what the Q is. So this is a problem that is not separable in a sense between theta and Q. Okay. And so typically one would have to think about how to approach this problem with optimal control. So what we are using is sort of a very nice argument that Jutta Teuker has developed to show that when the objective function is concave, though not separable in terms of its description of the virtual utility function, then we can describe the nature of the optimal solution without using control problems. We basically still can use local conditions, okay, pointwise conditions, okay. And so here's the idea, okay. So as we transit basically from a negative to a positive choice in terms of what the Q is, and so I might as well just scale everything by -1 or 1. We saw that there's going to be jump in the virtual values, okay? And what the theorem said is that basically there must be a Lagrange multiplier, okay, so that the two functions, the two virtual utility functions that we need to connect, need to be on the same side relatively to the Lagrange multiplier. And if they're not, then the solution must be 0. Okay? And so here, so these were the virtual utilities. The optimal menu in terms of the uniform, when the uniform distribution is being chosen, is the following one. So here we have the types varying from 0 to 1 and Q's varying from -1 to +1. Okay? There are now two steps, indeed, but the thing to observe is that there's really just one non-trivial information structure, namely the one that's offered to the interior types, which get perfect information. Right? Where the steps move to -1 or +1, this is the non-informative experiment. So what we see is now, this is sort of the solution that one would expect from the optimal monopoly pricing. The high value guys are getting the efficient allocation, everybody else is priced out of the market. Okay? And so indeed, there are conditions under which flat pricing is optimal. When the density is just on one side, so that's basically just the local conditions that matters. If the density of the types is symmetric, then again, we just get flat pricing because we are basically guaranteed that the adding up constraint is the same coming from both sides. And if they're always on the same sides, if the virtual utility functions are always increasing, then again, we just have flat pricing. Okay? But if you think about a Bayesian world, okay, one where we basically have information about the underlying state of the world, then it's not difficult to think that actually frequently the virtual utility function must be non-monotone, simply because in this example, there are more people a priori, or the state, the low state is here likelier a priori, and the agents have some information, so the uninformed agents are relatively few, they're more of the informed agents. Okay, that would give me a non-monotone function. If I'm simply thinking about a beta distribution, which simply expresses the fact that very few people are uninformed, most of them are informed, that is moved to the left or to the right, but they're not perfectly informed, then again, I would get a non-monotone density function and related virtual values, which I then have to iron, okay? And apart from ironing, then I need to patch them together so that they satisfy the integral constraints, and that's happening here, okay? So I'm basically trying to find a critical value, okay, such that I'm going to be either for both virtual utility function after accounting for the cost of the integral constraint, namely the lambda, I'm going to be either on both sides of the left-hand side or on the negative or on the positive. And if I'm not, then is where I need to use, make use of the global constraint. And so that forces me now to sometimes offer experiments that are here offered between basically 0.2 and 0.55 that leads to a Q that is negative. In particular, it means it's therefore a directionally informative experiment. I'm also going to offer an informative experiment, but I'm going to use both, the perfectly informative and the only partially informative experiment. Okay? And notice now here that because the weights are not symmetric in terms of the likelihood of the types appearing, what we do find is that the type 1/2, even though he's the efficient type, and he offers us the highest value, the highest surplus, is not getting the efficient allocation. So the efficiency at the top, that is now also not true anymore under global constraints, and so 0.5 gets an inefficient experiment in a sense it's only directionally informative and not perfectly informative. With this summary, which basically says that I'm going to bunch intervals. I'm going to just offer not only coarse experiments in terms of the few signals, but also I'm going to be offering a coarse menus in the terms of there being just few experiments. And if I have two types, if I have two states, then it will be that I'm at most offering two experiments, one perfectly informative, the other one not. Okay? And so what I hope to have shown here today is that the problem of sampling incremental information is sort of an interesting one. This has sort of basic features of a standard nonlinear pricing problem, but it has new elements coming in from the Bayesian nature of the problem namely that naturally the most valuable type is in the interior, and that incentive constraints are now going to appear in many directions. They are locally well defined, but they need to be accounted for also in a global sense, and that's what this last result showed you, how it's going to be resolved in terms of the nature of the optimal information structure. Okay, and so we see sort of interesting aspects of nonlinear pricing, both within groups, but also across groups or across directions. Okay, let me stop here.